Hi, my name is Abita Hawk, and today I will be talking about my proposal. Ring signatures are comprehensively post-quantum secure, even against active adversaries. There are a few terms I need to define for us to understand what this statement means. Ring signatures, post-quantum security, and active adversaries. Your security on the internet is underpinned by the security of cryptographic schemes. These cryptographic schemes work because we assume that any bad actors who are trying to break the security have access to a computer and maybe can talk to different parties over a network. But even with all of these abilities, they still cannot break the security of your scheme. So they can't, for example, open up your email or find out your identity if you wish to keep it hidden. Quantum computing threatens the traditional security schemes because the assumptions that we make for security are no longer valid. While there are many cryptographic schemes, I want to focus in particular on ring signatures. A ring signature means that there is a set of people and one of the parties in that set wishes to sign on behalf of that set, meaning they want to send out an authenticated message. In the example we have three people, Alice, Bob, and Charlie. And let's suppose that Alice wants to send out an authenticated message on behalf of the set. With ring signatures, she can do so, and anybody can check that it came from one of these three people. However, they cannot tell which exact person it was. There are many ring signature schemes that are provided in the literature, and they have different levels of security associated with them. When we go back to thinking about how this adversary might try to impersonate people in the scheme, or maybe try to view many signatures and then try to create a new authenticated message that looks like it came from somebody. These types of attacks are considered not possible in the classical setting. However, previous work has not considered what it would mean if there was a bad actor, this adversary, who could try to do these things with access to a quantum computer and quantum communication. Furthermore, certain works only look at very weak adversaries that do not consider all these different kinds of actions that he could take. Like I mentioned, impersonating or trying to create new signatures or trying to join the ring many times. There's all sorts of different attacks that can happen. So in my work, I propose to show a ring signature scheme which is comprehensively post-quantum secure even against active adversaries.
Let's spend a little bit more time with some technical details of ring signatures to understand them a little bit better. The first thing I said was that anybody could check that it came from someone in the ring. But how does that checking occur? Well, to know what the ring is, verifiers have access to public keys associated to the identities of each of the members. So, for example, a verifier has access to the public keys of Alice, Bob, and Charlie, where each of Alice, Bob, and Charlie have the corresponding secret key that they keep to themselves. Nobody without access to these secret keys can create a signature, which is what gives you this unforgeability. Nobody that's not in the ring can create a signature. The other aspect that we have is that nobody can see, which exact public key was used, and that's the concept of anonymity within the set. So again, here they have all these public keys, and the verifier knows that it came from one of the public keys because that's what they used to verify the signature in the first place, but they can't tell which public key was used. And now that we know what these security notions are in more detail, we can talk about actions that the adversary can take to try and break either unforgeability or anonymity.
Ring signature schemes should have the security properties of unforgeability and anonymity. To model these security properties, we think of an adversary who is given access to certain oracles. These oracles represent real-world actions an adversary might take in order to break the security. There's going to be 4 oracles. The first one is called Osign. Here, the adversary can request signatures to be made on a ring and view as many of them as he wishes. After all of that, he can try to either forge a new signature or try to de-anonymize from whom these signatures came. The next one is OKGen. Whereas previously maybe we were thinking about a ring that just is created at the beginning, maybe there's a possibility to add new members to the ring over time. Here, the adversary can request that new members be added to the ring. The next oracle is OCorrupt. Here, the adversary can request on those keys that he's been given that he learn the secret keys of some of them. In order to forge, he still needs to look at only honestly generated keys that haven't been corrupted, but maybe by learning something about other people's secret keys, he can do that. And the final one is ORegister. Here, the adversary can actually produce his own keys and add them to the ring himself. So we'll notice here that the actions of the adversary are more or less active in certain senses. If you only have access to Osign, where all the keys are produced ahead of time, this is less active than allowing the adversary to, in arbitrary interleave, add more keys to the system. And similarly, allowing corruptions of certain keys is less active than allowing the adversary to produce his own keys. And some ring signature schemes in the literature did not account for everything, as I've kind of alluded to here. So in order to have active adversaries, we really require all 4 of these oracles to be accessible by the adversary. The next part of adversarial power I want to talk about is the plain model versus the quantum random oracle model. In the plain model, we assume only falsifiable things like RSA, meaning that this adversary can at home try to break the RSA problem, and that will allow him to break the scheme. And that's all that we're assuming. RSA is not quantum secure, but we could replace it with a quantum secure problem like LWE, and the assumption remains the same. As long as the adversary can break this assumption at home on his own computer, then it would indicate breaking the ring signature scheme that we created. And in all cases, this amounts to breaking an algebra problem. Usually, relying only on these kinds of standard assumptions, in this plain model, makes it very difficult to actually have a provable security scheme. So we often rely on something called the random oracle model. The random oracle model is an idealized model of cryptography which assumes that for given inputs you get a truly random output. In the classical random oracle, there is this concept of just having a single input, let's say x, and the random oracle will just give you back y, which is h of x. However, this becomes a little bit different in the quantum random oracle because now, rather than having for a single x you get a single y, you replace these with superpositions over x and y. Meaning that in some sense the adversary can ask about all the x's that are possible as input and receive all possible answers as output. This model changes the way that we think about security and can cause different issues. This is actually why RSA is not possible to is not secure in the quantum model. And so this is a new consideration that we have to think about as we're producing these new ring signature schemes in order to show that they're comprehensively post-quantum secure. At this point, I have given enough background for us to understand what limitations of prior work are. One, the ring signature may not be efficient. I talked about the plane model earlier, and those algebra problems do usually allow us to have more efficient ring signatures in the sense that they're smaller. If you have n people in the ring, then you can have a ring signature that is perhaps O of log of n, which is better than having O of n. The other limitations, which I focused a little bit more on, were previous ring signatures did not have active adversaries, and previous ring signatures did not explicitly prove their work with quantum reductions. So they didn't assume that the adversary was comprehensively post-quantum and consider what that meant for their security proof. In addition to that, previous ring signatures did not have explicit post-quantum security definitions. So each time I talked about those oracles and how you would define unforgeability and anonymity by assuming that the adversary could have access to these actions, you should also consider what if the Osign query was also allowed to be done in superposition. And so these are things that, as we'll see over the upcoming slides, that I've worked and made partial progress towards, and there still remain some questions to be answered in this context. I do need to give one more piece of background information before we can look at my work, which is to talk about ring signature variants. The base definition of ring signatures are a signature within a set that is unforgeable and anonymous within the set. You can add on to this by having threshold ring signatures. A threshold ring signature means that rather than thinking that 1 of n people have signed, you can take it to T of n distinct signers. And the way that this is usually done is by having interaction between parties. So with Alice and Bob and Charlie as the ring, maybe we want a 2 out of 3 signature. So Alice and Bob talk to each other, and they'll both somehow use their secret keys to create a signature that a verifier can believe that it actually required at least 2 different secret keys to make. He won't know which 2 of these people, but he will believe that it came from 2 out of 3. Another trickier way to do this is with Intersigner anonymous ring signatures, meaning that each person can create their own signature, and then there's some way to check to see that it came from different people. This is considered better because how are you going to get a threshold ring signature if you don't even know who wants to join your signature in the first place? This way, we can just concatenate new signatures as they come up and create a threshold in a more flexible way. One way to do this is by having a link algorithm, where a link algorithm takes in 2 1 out of n signatures and the message and ring, and will output 1 or 0 telling you if it came from the same signer or not. A more stringent definition would be to use a trace algorithm, which on 2 different signatures and the message and ring actually outputs the identity of that person or tells you if they're independent. So linkable and traceable ring signatures are one way to get Intersigner anonymous threshold ring signatures, although you can also think about them as being ring signature variants in their own right. Finally, we can talk about my work, what I have accomplished, and what there is left to do. My first work, chronologically actually, is a problem called Threshold Ring Signatures, New Definitions, and Post-Quantum Security. That's where I first approached the idea of having active adversaries and providing post-quantum reductions. However, this work still has a limitation, in that it does not allow for comprehensive post-quantum security, so the other oracles are not post-quantum. So Osign is not post-quantum. The only thing that this includes is having the quantum random oracle. So one problem that there is left to do is to make it more comprehensive by making all the oracles post-quantum. And one way to look at doing that is to take this other work, which is called one-time traceable ring signatures, which is a much simpler way to do ring signatures, and to add the oracles there. So this paper also is not post-quantum. In fact, it does not have the quantum random oracle, but upon looking at it, it seems that it should be possible to do this. And that would accomplish a more comprehensive ring signature scheme that allows for access to oracles that are quantum. One more thing that we noticed is that in my first work, that one of the nice things was this threshold ring signature that I did was actually quite general. Meaning that rather than relying on a specific problem, not like LWE or RSA, of course, I relied instead on more general assumptions. And that means that I created more of a scheme, meaning that something that people could plug in their particular instantiations of my hardness problem and create a particular threshold ring signature as a result. The one-time traceable ring signature is not as general, but it does have assumptions that seem like they could be generalized. So here, one of the things to do is to generalize this work, and in the end, what we hope to get is a comprehensively post-quantum traceable ring signature that is proved in the quantum random oracle model. And this is work that I'm currently doing with Jan Tchaikovsky, and we're about halfway through. We have some post-quantum definitions for the oracles, and we still need to work on the actual security proofs. So that leads us to our first two research questions. One, how can we make a compact traceable ring signature, and possibly in the plane model? So currently, Jan and I are working on a traceable ring signature, but it's in the random oracle model and it is not compact. So a way to extend this work would be try to make it compact and to try to put it in the plane model. So those are kind of stretch goals. The second question is, can we achieve a post-quantum secure ring signature scheme which allows all oracles to be quantum? So far, this question seems very positive based on the work that I've done with Jan so far, and so we hope to have that paper finished and actually answer this question quite soon. The next work that I have is my work on logarithmic size threshold ring signatures in the plane model. Now, this paper achieved logarithmic size ring signatures, or compact, as I've called it before. So it was actually O of log n per signature, and with a threshold of t, that's just a concatenation of t of those, so you would get O of t of log n size signatures. And the other nice thing is that we were able to achieve the plane model rather than the random oracle model. However, the limitations on this paper were we were so insistent on being in the plane model that it gave us a weak definition of unforgeability. In particular, we were not able to allow an adversary to register his own keys in the ring. This also appeared throughout when we showed how to extend our work to linkable ring signatures, because linkable anonymity and linkability also had problems in that you couldn't register you couldn't have an adversary register keys and still maintain those new properties. So the to-do here is to see, can you achieve fully powerful unforgeability, so unforgeability that allows registration while keeping everything in the plain model. If not, we can try to answer the question using, of course, the QROM, or potentially do this in another kind of model entirely, which is called the Common Reference String, or CRS model. These tend to be a little bit easier to deal with, but it would be nice to see if it's possible to do in the plain model. So that leads to my third research question, which is, can we have a compact ring signature that allows for users to potentially maliciously register their own keys? And as I asked, is it possible to do it if we allow trusted setup, that is, by having a random oracle or having the CRS model? And that should be possible. It seems positive. So the stretch goal is to say, is it possible to do it in the plain model? The last thing I want to talk about is kind of a bonus question, which is not ring signatures directly, but the generalization, which is anonymous authentication. Here, you might have, rather than having a ring where anybody can join at will, you might have a group manager who allows you to join and gives out keys. There are different notions of security in this sort of scheme. And I do have work which talks about device authorization for cellular networks, where we actually assumed that there was a manager, a registry manager, that gave out keys, but you could still do a 1 out of n signature as a result. So the question is, given that I've answered these other 3 questions, what are the natural extensions towards group signatures or other forms of anonymous authentication that we might want to have? So that covers my last question, which is, how do the results associated with ring signature apply in other settings where there is a trusted manager or setup? And with that, I have covered all 4 of my research questions, what I've done towards answering each of them, and what there is left to do.